important thing. I realized yesterday when I went home, actually when I was already teaching I realized there was something wrong, but then when I went home I checked better. So this equation here, that we discussed yesterday, was actually wrong. So now I posted on the website was just one slide with the equation corrected. So when it comes to calculate the distribution of the lateral forces in our walls due to the torque moment due to the seismic action, yesterday I showed some equations that were wrong because some terms were missing. So if you want just to pay attention, just a minute. Okay, this is Dr. Ciotti telling me about an issue with you three. Now, just a moment, please. Pronto? This introduction. I was telling you that before, yesterday, I showed some equations that were wrong. So, see this two equation here. Yesterday, some terms were missing. So yesterday I showed an equation where there was this L without this bracket here, divided by the summation of L times the bracket without the square. Okay? The right equation is this, so you can see here. So if you want, you can correct the equation that I showed yesterday by add these two brackets as the numerator, and by add the square in the brackets at the denominator. Anyway, I uploaded on e-learning just one slide like this with the right equation. Okay, so you should substitute this slide with the other one. Of course, it's not possible because you printed with the whole presentation, but anyway, this is the right equation. Okay? This equation is formally the same or very similar to the one that we derived for calculating the shear force in a bolted connection subjected to a torque moment. In that case, we had the distance squared, while instead here we have this, we have an R, which was the inclined distance, while here we have this, let's say, parallel distance, parallel to the x and to the y axis. Okay? In the other case, this L was equal to 1, while instead here we need to take into account the stiffness, which in the case of the bolted connection, we assume that all the bolted have the same stiffness. Here instead the walls may have a different stiffness because the stiffness is related to the length. So the longer the wall, the higher the stiffness. So we need to take into account the L, which replaces the stiffness. So next year, when you are going to attend a course called Masonry Construction, you will find out a similar equation, probably also in seismic engineering, you will derive this equation here, where this L will be replaced by K, which is the stiffness of the wall underneath. Okay? In our case, we said, since the value of stiffness in our case would be fairly complex, because it would depend by, if you remember, all the different components of the tension, the rocking, the slipping, and so on. We do a simplification, we replace the stiffness with the length of the wall. In other words, the stiffness in our case is proportional to the length of the wall, so we can replace the stiffness with that. Okay? To do a simplified approach, to follow a simplified approach. The same that you will be following in this exercise. Okay, now we go back to this work example that we saw yesterday. If you remember yesterday we got up to this point here, so first yesterday we calculated the seismic wave. So this was basically the load assessment. We calculated the seismic wave. Then we calculated the natural vibration period of the building by using this simplified equation. So the natural vibration period of the building is 0.05 times the height to the power of 3/4. The new regulation will actually suggest a different relationship. 2 times square root of t, where t is the lateral displacement on the top of the building. So this will be the lateral displacement on top of the building due to the seismic load condition. The problem with using this equation is that we could use once we have already designed the building. Because you see, in order to get this equation here, if I have a building like this, and I know the different seismic forces here, in order to be able to find here the total displacement, so D would be this basically. In order to find this total displacement here, I need to have already designed the building. Something that when I'm designing the building, of course I don't know. So the problem of this equation, first we need to do a preliminary design of the building. But to do the preliminary design of the building, I need to have an estimate of T, because otherwise I don't know the value of ST in the design spectrum, because the design spectrum depends on T. So T depends on D. So you see, it's a kind of closed loop, because to calculate D, I need to know the forces. But the forces depends on T. And T depends on D. So how can we break this loop? The idea is that we should use this formula here, which was the old formula from NTC 2008, and which will be also recommended by Eurocode 8. This formula just depends, as you can see, on H, on the height of the building, which we know, of course. So we can calculate T1, and once we calculate T1, we can estimate all the lateral forces. Once we know the lateral forces, we can design the whole building. And at that time, if we want, you can calculate D, and then you can recalculate T1, you can recalculate all the forces, perhaps to refine a little bit better the design. Okay? But for sure, we need to start in this way. So, for our case, if we replace this H with our value, we get 0.28 seconds. Okay, and now it comes to calculate. I don't want to exchange it. So, elastic design spectrum. Now, of course, when it comes to calculate the elastic forces, we need to take the regulation, either the Eurocode 8 or, if you are in Italy, of course, the Italian regulation. We can also use, as I told you before, the Eurocode 8, but with a national application document, which is basically which is based on these values that we can find in our technical Italian regulation. So, as you already know, we need to take these three values here: the maximum horizontal acceleration, the maximum amplification factor of the spectrum, and this value of the vibration period, which is on the boundary of the constant velocity part of the spectrum. So, we need to make some assumption for this value. For example, if we assume that we are in dell'Aquila, we can get some value. In this case here, I just took some values, for example, AG 0.35G, F0 2.5, and TC asterisk 0.5. There is, as you know, a document giving you those three values for each council in Italy. So if you go in this document and take l'Aquila, you will find three values that you need to use for the design if you want to do your design here in l'Aquila, of course. Then you have this equation. This is the elastic spectrum, which, as you can see, depends on the natural vibration period. Depending on the value of the natural vibration period, you have different equations for the elastic spectrum. And then here you have different coefficients. So, for example, the spectrum depends on the kind of soil. In our case, we assume that SS and CC is 1. Then you have this topographic coefficient. If you are on the top on the summit of the hill, like here, you have an amplification 1.2, as you can see. So here we assume to be on the top of the hill, so 1.2. And then you calculate this different value S 1.2. TC becomes 0.5, TD 0.17, and TD becomes 3 seconds, and eta 1. So once you calculate your elastic spectrum. You enter the elastic spectrum with the natural vibration period, or the estimate of the natural vibration period that we did with the equation we saw before, and we find out, you see that we are on the top of the plateau of the seismic, of the elastic spectrum. Then there is this chapter from NDC 2018 saying that for the seismic demand, if we perform a linear elastic analysis or a linear dynamic analysis, we can use the formula that we saw before by assuming for eta 1 over Q, where Q is the behavior factor. So in the end, for T in the range between TB and TC, which is our case, SET is the elastic value of the spectrum, and SDT is the design value, is the value of the design spectrum. So the one that we are going to calculate in our case. So SDT is AG, which is the peak ground acceleration, times S amplification factor. So AG is 0.35, S is 1.2, F0 is F0 is the amplification factor, which is 2.5, divided by Q. We assume in this case to have a cross-lamp building, so we use the value that will be proposed by the new Eurocode 8, which is 3. In your case, you should use, I would say, 2.5, because the value that is recommended by the Italian regulation. So SD, the function of T1 is 0.35. So in the end, as you can see from the black curve, which is the elastic spectrum, we can move to the blue curve, which is the design spectrum. The difference between the two is that the black one is used when you do an elastic analysis, while instead the blue one is used when we do, let's say, a classic analysis, in the sense that we have a dissipative structure. So a structure that can dissipate energy with a Q factor of 3. So for us, this is the value that we are going to use in our design. Obviously, we will now design the dissipative part of the structure using these seismic forces, but then we need these reduced seismic forces, but then we need to use capacity-based design to carry out the design of the brittle part of the structure. So the brittle part of the structure will be designed not by this force, but by the overstrength of the dissipative components. So, base seismic shear, so now we calculate what we call the base seismic shear, this value, FB. So the base seismic shear is SD, what we have just calculated, 0.35 times the seismic weight, 710. So we get 248.79 kilonewton of total shear on the base of the building. Now we need to distribute this total base shear above the different story. So the calculation of the story seismic forces is done with this equation, FB times MI. So for example, this one is, we have a mass here, MI, and this is the distance, ZI, so the distance, the height of the story from the foundation, and this is what we call Fi. Okay? So with this equation here, we calculate the 3 seismic forces. In our case, it will be 2, no, 3, because we have 3 stories, so the 3 seismic forces are the different stories of the building using this notation, this equation here. So, here we have the different seismic weights of the different stories. So, the roof is lighter, then we have the second floor and the first floor. FP, this is the total seismic shear at the base of the building. This is the height of the different stories, so 3.09, 6.8, 9.40. And then in the end, we get these 3 forces here, F3, F2, F1. As you can see, F3, in the reality, we have a situation like this. So F3 is slightly smaller than F2. Why is slightly smaller? Because the mass of the roof is smaller than the other masses. Because on the roof, if you remember, we have the snow, and the snow is not considered in terms of seismic weight. So the assumption is that when the most severe seismic action occur, statistically there won't be any snow on the roof. Okay? So for this reason, this force is slightly smaller. And then once we have the seismic force at a different story, we can calculate the seismic shear. The seismic shear would be the sum of those forces. So it would be a plot like this. So this is the seismic shear. So T3, T2, and T1. Where T3, of course, T3 is equal to Fp. Okay? So one important thing is that when we are going to design the wall, for example, a generic wall, so what I said yesterday, in this second design project you should carry out, the idea is that you should design only one wall. So not the whole wall of the building, only one wall, let's say the most stress wall. So this wall will be like a cantilever, going from the foundation to the top. And this wall will be subjected to a part of this seismic shear, because this is the resultant seismic shear acting on all the walls. So with the formula that I showed before yesterday, we will have to redistribute this total seismic shear among the different walls of the building. So here you will get in the end something like this, a plot like this, which will be the seismic shear of the J wall. Okay? Of course, this seismic shear of the J wall is just one part of the total seismic shear, because the total seismic shear is the resultant of the seismic shear of the N walls that I have in my building. So I will move from this seismic shear to this one using the formula that I showed before and the formula that we showed yesterday. Okay? Okay, let's yes, you're right. Yeah, according to this notation here, this is T3. So this is F1, Fi, F3. This is T2, and this is T1. Sorry, this is right. This one. Okay. So the connection, so how we move from this to this is using, as I said before, this formula. For example, the formula we saw yesterday, if we call this one but we should call this, for example, T1J. So T1J will be given by L1J divided by summation of L1J of T1. Okay, if you remember yesterday we saw that if the seismic shear is applied in the center of stiffness, then we can calculate the shear in the wall J using this equation here. Okay?
Why the shear is constant for the first and second floor?
What is constant? No, it's not constant. Well, so let's see, what is it constant?
No,
this one is constant, the seismic weight. The seismic weight is constant. So the seismic weight, which means the mass, if you want. So this one is the same as this. Instead, this one is smaller. But the seismic forces, you can see, they are not constant because this mass here, which is the same as here, is higher.
No, the shear.
The shear is not constant. Well, the can see it's constant. It's just constant between this section and this section. But then once you move above the floor, then it moves. You see, there is a discontinuity here. One is here, the same here and here. Discontinuity, and then discontinuity.
Non si vedeva adesso.
No, because it was hidden. Okay? It's clear, this is an important concept, but we'll let you understand the level of the formula, because this is just the basic of involved seismic design of building. More or less the same thing that you apply for your frame in reinforcement design. Yes? Yes, then when we talk about the mass, the seismic weight, like we said yesterday, the seismic weight is basically the mass of the floor plus what is above the floor, so plus the mass of the content. When it comes to the wall, what we do usually, the wall I'm talking about partition, we assume that half of the wall above the floor and half of the wall below the floor of the partition are considered when I calculate the mass of a generic floor. Okay? In fact, on the roof, we have only half of the wall, the half of the wall that are below the roof. On the foundation, this half of the wall, they insist directly on the foundation, so they are not considered in the seismic as a seismic weight, because they basically insist directly on the foundation. Okay? If you remember yesterday, here, I will also show you where. Here, you see, so this is the mass of the floor, then this is the mass of the wall. So 2.8 times 6.9 times 4, this is the mass of 1, 2, 3, and 4 wall, which are considered entirely, so they are multiplied by 2.8. Oh, where is it? No, sorry, 6.935 is the length. Yes, 2.8 is the weight of the wall ranging on the whole height per unit length. So this one is this would be the weight per unit length of the wall on the whole height of the building. So they are considered with the whole value in the first and second. For the roof, you see that there is divided by 2. Yes, but then a partition of this one. But in this case, they are all structural. In this case, now in our case, instead of partition, they are all structural.
Nothing changes if the next part not structural.
No, usually you always do this this kind of bulk convention to assume half above and half below. It's an approximation. So which other question you have? Yes, 7.93 times force, 1, 2, 3, 4. Okay? Then here, this one is what is it here? 2.4 by 2 because 1 and 2. Okay? Clear? Any question? Okay. Okay, now to move from T3, T2, and T1. So from this diagram here to this one, for the different wall, we need to use either the formula that I showed yesterday, which is what we were supposed to do it, for one wall again. You should do it, well, you should identify the most stressed wall based on the equation. So basically you should do the redistribution among all the walls, but then you should decide only one, the most stressed one. Okay? So, to move from this one to the wall, either we use those formula, or there is a software that has been used in this case, which is which does nothing else than basically applying the formula that we saw yesterday. Okay? If you want, this is a very simple software, hand-done software that uses basically just the formulas that we saw yesterday. See, assumption for the analysis in plane rigid floor diaphragm, shear stiffness per unit rate of wall, constant for all the wall. So we assume that basically the stiffness is proportional to the length of the wall. So the longer the wall, the higher the stiffness. Okay? In this case, this is the result, the contour of the seismic shear forces per unit length of the wall. So you should get to this result here using the formula that we saw yesterday. It's clear? Of course, if your seismic force is applied in the center of stiffness, then you just use this equation here. If your seismic force instead is not applied in the center of stiffness, you need to use also the other equation that I showed this morning, the one that was wrong. Okay? So you can see here, for example, that this is the contour of seismic shear force per meter of wall. So TSD. So in this diagram here, TSD is basically Pij divided by Lij. Okay? So TSD here denotes the shear in the wall. So the total shear in the wall divided by the length of the wall. So this is the total shear per meter of wall. Okay? So in some way, we are, in order to design the most stressed wall, we are not so much interested in Tij, but in the ratio between Tij and the length of the wall. Because this is where we will have to provide more connections, basically. Okay? So we do this division. And for example, in this case, you see that these two shorter walls are the most stressed one. So in this case, what we are going to do, we are going to design the most stressed one. Of course, in the real life, we will have to design all the walls. But as I said, in order to reduce the time that we have to dedicate to this project, we are going just to take into consideration, just to design one wall, the most stressed one. That here is identified as these two panels there. Okay?
We analyze all the wall and then we choose.
Yes.
Or we can take it out with this wall.
No, because you don't know, until you don't use this formula here, you don't know which one is the most stressed one. So you need to do the distribution of the forces among all the walls. Then you divide the forces by the length, and you take the wall that has this ratio as the maximum. And then you design this one, only this. Okay? So which verification, now that we have identified the most stressed one, which is this, which verification do we need to do? So, ultimate limit of strength for uplifting of the wall downs, ultimate limit of strength for shear of the anti-brackets, the ultimate limit of compression of the most loaded walls. Okay? Those are the three equations, those are the three verifications that we need to do. Okay? Oh, this is a private problem. It's something that not me actually, a collaborator of mine did using in-house software. Yes. It's basically just a translation with some graphics of the equation that we saw yesterday. There's nothing more than the application equation. Doesn't mean. So if you do by hand, you should get exactly the same result. There's nothing that you can get any other. Okay, now in the design, of course, we need to, when we design the hold downs, we need to choose the hold down. So we go to see some catalogs, For example, there are catalogs available online, like the catalog from Rotoblast. I don't remember if I uploaded the catalog of Rotoblast. Maybe I'm not sure. Anyway, you can download it freely from the internet. You just digit Rotoblast. It should be something like this. Don't remember if there is an H here, maybe. Don't remember. You go online, you just digit this. They have some catalogs available online. You just download. There are huge catalogs. In these catalogs, you can find some information about all sorts of connections, from nails, screws, also hold downs like this. So there is this hold down here, which is denoted by WHT620. You see here, with the sizes. This one is the H, the different, the length, the PS, and here 52. This hold down here has 52 nails, 60 millimeter length and 4 millimeter diameter, and one 20 millimeter diameter anchor bolt to connect to the foundation. There is already some information here in this line. If you look at the last line, you get the permissible load current capacity, so still using the permissible stress method, and also the characteristic value of the load current capacity. So the characteristic one, you have a value of load current capacity, characteristic load current capacity on the wood side, 100.4 kilonewton, and on the steel side, 85.2 kilonewton. So this one is related to the failure of this connection. This other one, 85.2, is related to the failure in this neck area of the plate. Okay, basically failure for tension. So we already got the value that we need. Then we need to choose a shear connector. For example, this 110 by 90 angle bracket. So here there is the property of this angle bracket. So we have 11 4 millimeter diameter, 60 millimeter long anchor ring shank nails to connect the angle bracket to the wall, and two 12 millimeter diameter anchor bolts to connect this other side of the angle brackets to the foundation. Also here we have a characteristic value, which is 12.7 kilonewton. Okay, so those values are all provided by the producer. Then we can think about using some, for example, 8 millimeter diameter, 80 millimeter long self-drilling screws at 150 millimeter center to center to connect the walls, the vertical walls along these joints. And 10 millimeter diameter, 180 millimeter long screws at 75 millimeter center to center to connect the walls on the corner. Now let's go to see the uplifting verification of the wall one. So we said that the most stressed one was this wall here on the base. So if we apply on the top of this wall the shear, which is the maximum shear, so TST times H is the overturning bending moment, minus the stabilizing bending moment. Stabilizing bending moment is Q, the vertical load that we have due to gravity, because those panels have two functions. One function is to resist to the lateral load, and the other function is to support the gravity load, because they are supporting also the flow. So the gravity load is stabilizing in this case, because you see that the result of this vertical load multiplied by B over 2 will give us a stabilizing bending moment. In fact, if this vertical load is very high, you wouldn't even need a hold down, because it would be stuck. If this second component is higher than the first component, theoretically you wouldn't even need a hold down, because the vertical load would be enough to prevent this uplifting Okay? Obviously, even in this case, we have to provide a hold down, because we can't have an unstable structure. Okay? So, the design force in the hold down would be TST times, so basically the seismic shear times H divided by B minus Q, this load per unit length, times B divided by 2. TST for us is, so the total shear, because the total shear is actually, the total shear is the shear per unit length that we assessed before, times the length of the wall. So if we replace now these symbols with the numbers, in our case we have TST 23 kN per meter times 1.47, the length of the wall, times 2.95, the height of the wall, divided by B, and the length 1.47, minus 60.5. So 60.5 is the vertical load per unit length. Now we're going to calculate this value, times 1.47 divided by 2. We get 23.4. Now how do we get 60.5? 60.5 is the gravity load per unit length acting on this wall. So if this is the building, this is the wall that we are designing right now, and of course we need to find a kind of tributary area of the floor which download its weight on the considered wall. So on this wall, of course, we can assume that this wall here is taking half of the total load acting on this floor, because this other one will take twice, and of course this wall half of the half, so 1/4. In the end, if I consider this tributary area here, this tributary area is 1/8 of the entire building area. So this wall will support 1/8 of the entire area of the building considered. So I just take the total seismic weight and divide it by 8. Okay? Because this is the total seismic weight, but this one is taking only 1/8. So in this way I get 88.9 kilonewton. 88.9 divided by 1.47, which is the length of the wall, is 60.5 kilonewton per meter, which is the value that we have used here. Okay? Now we do this uplifting verification of the wall panel. We said that we are going to use this hold down, WHD 620 with 52, 4 times 60 ring shunt nails, and 1 anchor bolt 20 mm diameter. So this is the hold down which is provided by default by Rotoglass. Okay? So, ultimately the state of shear strength of the nails. Then we need to check the ultimate state of shear of this nail connection. Then we need to check the ultimate state of tensile strength of the anchor bolts to show that these anchor bolts won't fail in this weaker cross section. And then the ultimate state of tensile strength of the hold down metal plate. So, in the end, limit state of shearing of the connection, tensile strength of the anchor bolts, and tensile strength of the metal plates in the weaker cross section. So ultimately, state of shear strength of in general, for example, of the nails. The normal equation for a timber building is K-mod times RK divided by gamma n. So the K-mod for seismic verification is 1.1. So seismic verification is considered as an instantaneous loading. Even though it is not instantaneous, it will take some seconds. But the K-mod is actually equal, this K-mod considered equal to 1.1. Of course, we need to remember that in which seismic class we are. In a building, inside the building, we are seismic class 1, for sure. So 1.1 is our coefficient. Then gamma n, safety coefficient. According to the new regulation, to the Eurocode 8, we should be using the gamma n coefficient of basically 1. However, if you look at the Italian regulation, as I already mentioned, said that we can use gamma n equal to 1, which is the partial safety factor for accidental loss situation, only if we consider the degradation of strength due to cyclic actions. So we should basically reduce the strength of the hold down to take into account the real cyclic action rather than a monotonic action. Since we are using basically Johansen equation, and anyway, the values that the producers provide for the hold down are not reduced to take into account cyclic action because they are just taken from static test. According to the Italian regulation, we cannot use gamma m equal to 1. So we need to use the gamma m that is suggested for fundamental load combination, so 1.5 in our case. Okay? Strictly speaking, I would say now, here it was used 1.5, now we could use 1.45 because with the new NTC 2018, it was clarified that for blue lamp and cross lamp, we can use 1.45. So, in your design, what you can do, you can reduce this 1.5 to 1.45 for a cross lamp building. So this was done with the old regulation, the NTC 2008, where there was no provision for cross-lamp. Well, instead, the new one now has provided some information for cross-lamp, and it said cross-lamp can be regarded as blue lamp. So gamma n 1.45. Okay? Okay, so now, how do we perform this verification for the nail connection between the hold down and the wall? First of all, we need to remember, is this nail connection a sympathy connection for us? If you remember, for a cross-laminated building, we said that the sympathy connection are the connection between the hold down and the wall, and between the angle bracket and the wall. So this is considered as the sympathy one. So we can design it for the value of the forces that we obtain from the seismic shear using the Q factor of 3. Okay? So RD, the resistance, shall be greater than or equal to the shear demand. So RK for us is the value provided, 100.4 is the value provided by Roto Blush. If you go back again, you remember we said that from the catalog of the producer, you see by using this hold down here, the characteristic value of the connection between the nails, so the hold down, the nail connection between the hold down and the wall is 104 kilonewtons. So this is the characteristic strength. So the design strength will be so 100.4 times K mod, which is 1.1, divided by the material safety factor. That could be assumed 1.45 now instead of 1.5. So we get 73.6 kilonewton. So 73.6 kilonewton is the strength capacity of the hold down inside the condition. This one should be greater than the strength demand. The strength demand is the value that we calculated before. Strength demand is this one, 23.4 kilonewton. Okay, so we check. 73.6 greater than 23.5. So the verification is satisfied for the dissipative zone. Then we need to check the metal plate of the hold down. You see here, you see this kind of failure mode. This is the failure mode that we want to avoid. The failure mode for tension in the weakened cross section of the hold down. Okay? Now, the metal plate of the hold down, is it a dissipative part of the structure or a non-dissipative part of the structure? It's non-dissipative, it's a greater part of the structure. So if this is a non-dissipative part of the structure, how do we design this part? with an overstrength. So we need to design this part, not for the demand, not for the 23.4, but for the overstrength of the dissipative part of the structure. Okay? So you see, the metal plate of cool down is not designed to take 23.4. So glad that this is clear to all of you. So this kind of metal plate is not designed for 23.4. Remember, 23.4 is actually the strain demanding load down due to the seismic forces. But this applies only for the dissipative part. Since this is non-dissipative part, I need to take the actual strength of the dissipative connection, multiply it by the overstrength factor, and then design this metal plate for this action, not for the seismic one. It's clear? So, I need to take, you see, the actual strength. So the actual strength is 73.6. Okay? Actually, 73.6 is not even the actual strength. This is the design strength. The design strength is 73.6, but the actual strength is not 73.6. The actual characteristic strength, which value is the actual characteristic strength? You see that the actual characteristic strength is 100.4. So 73.6, I need to multiply by 1.5 by the partial safety factor to get the characteristic strength. Unless the 1.1. There is this 1.1 difference because during an earthquake we can assume that our structure is a little bit stronger. So 73.6 times 1.5 is the actual strength, and then I need to multiply by the overstrength factor. The overstrength factor for a cross-line building is 1.3. So I get, you see, 143.5 kilonewtons. So there is a huge difference between designing the hold down, the metal plate of the hold down for the actual seismic design, 23.4, or design it for the actual strength of the dissipative connection. The actual strength of the dissipative connection is 143.5. And as you can see, 143.5 is greater than 85.2. 85.2 is the strength that the producers gives for this one down here. So if you look before, go back again. So look here. The producer said that the characteristic strength on the wood side is 100.4. The characteristic strength of the steel side is 85.2. So the steel side is 85.2, the actual strength, but our demand using capacity-based design is by far larger than 85.2. Is 143.5. So this means that this hold down is not well designed for making its job as a hold down in the structure. Okay?
In this case, too, is 1.5.
Which one? 1.3?
No, 1.5.
1.5, this one, is the partial safety factor. So I need, see, your case will be 145, yes, exactly. According to the new regulation, this would be 145 instead of 1.5. Speak about. No, strictly speaking, there is a difference. Actually, you're right, because the new regulation has changed the material partial factor for cross-lamp. However, the material partial factor for connections is exactly the same. So what does it mean? That what I told you before, the 1.45 is not true actually. So when I check a connection between a metal plate and cross-lamp, or if I check a connection between a metal plate and glue lamp, or a connection between a metal plate and solid timber, the material partial factor is always 1.5, it's always the same. So sorry, I made a mistake. So this one shall stay 1.5 actually. Instead, the only one that will be changed is when we check the cross lamp. For example, when we check the cross lamp for compression, this can become 1.45 instead of 1.5.
Only for connections.
Only for connections 1.5. For any sort of connection, so connection between cross-lamp and steel, cross-lamp, glue lamp, for the connection is always 1.5. Also with the new regulation. But instead, at the material level, if I do a verification on the cross-lamp itself, for example, compression the cross-lamp or bending the cross-lamp, then I can use 1.45 instead of 1.5. Okay?
1.45 for metal.
It depends which timber. If it's some timber, it's 1.5. If there is some timber. If there is glue lamp and cross-lamp, 1.45. Exactly, yes. But only at the material level, not in the connection. The connection is always 1.5. So what I wanted to tell anyway is that this cross-lamp, this hold down here, it is not well designed for seismic action, or at least not for cross-lampability. In fact, you can see here that when we perform some tests, some real tests, instead of having the plasticization here of the net, we had a failure like this, which is what we didn't want. Because with a failure like this, which is the value of the behavior factor we should have used?
2.5.
No?
1.5.
1.5. 1.5, exactly. Instead, then 3 or 2.5. Okay? So, how can we solve this problem? To comply with capacity-based design, we should either increase the metal thickness, the thickness of the steel, by how many times? You see, by 143.5 divided by 85.2, because 85.2 is the actual strength on the steel side, and 143.5 is the actual strength demand. So this ratio is 1.65 times, which means that I should either increase the thickness of the steel plate by, let's say, 1.7. Okay, so 70% more, almost double. I should almost have to double the thickness of the steel in order to avoid this kind of failure. This is one option. The other option, if I keep the thickness constant, I should reduce the number of nails. How many nails less? Need to do. If now I have 52 nails, I need to multiply 52 by 85.5 divided by 143. So basically, I need to divide 52 by 1.68. Instead of 52 nails, I should just use, let's say, 30 nails, 31 nails. If I use only 31 nails, the system works because it is less strong, so at least less strong on the connection side, meaning that this connection can plasticize before I have this kind of failure. Instead, if I use too many nails, they will remain elastic and we will have a failure like this. Okay? Why was this hold down not well designed? Because when they developed, Professor Cecotti and other researchers developed the first cross-lampability, of course there were no connectors available. They just took the hold downs that were used for light frame construction. But in light frame construction, we learned yesterday or the day before yesterday that the hold down is always non-dissipative. So the problem in the hold down for the lightweight structure is that it's not a problem because there I don't have to ensure plasticization of this nails here. Any sort of failure is fine because anyway this one is non-dissipative. Okay? Instead for the cross-lampability, this should be dissipative, which means that I need to change the geometry of the hold down, either reducing the nails or increasing the thickness of the metal plate. It's clear? Okay. Now, second kind of verification, shear verification of the wall panels. So now we need to ensure that the wall panel doesn't slip, doesn't move horizontally, using this under bracket. So the under brackets, I calculate the design strength of 12.7, which is the strength of one under bracket, times 1.1, K divided by 1.5, 9.3 kilonewton. How many under brackets do I need to use to resist the actual shear strength? So, if I consider 4 angle brackets in this wall, so the design value 9.3 times 4 divided by L, the length of the wall, will give me 25.3 kilonewton per meter of shear resistance that I have to compare with the shear demand. The shear demand is 23, so you can see that with 4 angle brackets I can ensure that the ultimate limit state is satisfied. Okay? Last check that we do is ultimate limit state of compression of the walls for the overturning moment due to the seismic force and the effect of the gravity load given by the seismic wave. So now I want to check the resistance of the wall panel itself. So I take this one, which we said is the most stressed wall panel. We call with the A parete, basically the area of this wall. I need, as usual, to consider the tributary area. And then I need to go to calculate what is the value of basically the stresses that I can expect in this wall when I have this overturning, this possible overturning due to the seismic force. So, what I'm now trying to do, I try to check if when I have the seismic force acting in this direction. So now I'm doing a verification not for the seismic forces that were acting in the plane of the wall, but for the seismic forces acting out of plane of the wall. So I apply a system of horizontal forces, seismic forces are acting in this direction, and I'm going to check what is the stress that I can get in this wall due to the overturning bending moment that I have due to the seismic forces acting out of plane, so acting in the y direction. In order to calculate this stress distribution, what we have to do, we use basically the formula for bending and axial force. So M&MoCS is the seismic, well, if you want, it's the overturning forces due to the horizontal seismic forces. So this M&MoCS would be the global bending moment that I apply on this building at the base due to F3, F1, F2, and F1. So it would be F3 times H3 plus F2 times H2 plus F1 times F1. So this is, if you want, this M&MoCS is the total overturning seismic moment, which could basically make this building to overturn. Okay? So this total overturning bending moment is taken by this wall in plan. The most stressed wall will be obviously this wall at the edge, because this is like having a cross section done in this way. This is like checking a cross section like this, subjected to a bending moment like this. Okay? So we consider this as a resisting cross section. If we want to calculate the distribution of sigma, that will act on our cross section. So we use basically the linear formula plus this axial force coming from the gravity. So MEDS is the total overturning the moment. J base X is the second moment of area of this cross section with respect to the X, the neutral axis, with respect to the central axis X, times L divided over 2, the distance, because we want to check the maximum stress. The maximum stress is here, so this is the maximum stress. So we need to consider L over 2 plus this is the axial force so this is the axial force acting on the wall divided by so W times the area, the tributary area divided by the total area, so this is the total axial force acting on this wall, divided by the area of the wall itself. So basically this is 1/8. If we have if our wall is made by 3 layers of planks, we know that the resisting layer will be only 2. So the 2 layers with the wood oriented parallel to the grain in the vertical direction. So using 20 plus 20 plus 20 millimeter instant panel made of T10 boards, MDS will give us 1,608 kilonewton per meter. J base. So this is the second moment of area of this cross section with respect to the x-axis. So J base is so 0.6, 0.6. This is the total thickness of the wall panel. Of this we need to take only 2/3 because 2 layers are reacting and over 3 the other one is not reacting, so it's 2/3 times 0.06 will be 0.04 times this is the length of these walls here. So this wall here is 6.935 minus twice the thickness minus 0.06 times 2 to the power of 3 divided by 12. So in other words, this contribution is the second moment of area of this vertical rectangle with respect to the x-axis. So what we've done now is the second moment of area of this part of the cross section. Times 2, because we have also this one. Okay? So now we've done the second moment of area of these two rectangles with respect to the x. So B h cubed divided by 12. Okay? And then we need to add the second moment of area of these elements with respect to x. So 4 elements, 1, 2, 3, 4. 1, 2, 3, 4, 4 elements, times 2/3, because only 2 out of 3 layers are resisting, times 1.468, which is the length. So this is 1.468 times 0.06, the thickness. So basically 1.468 times 0.06 is the area of the wall. So the area of this wall here, times the distance from the x-axis. So 6.935 divided by 2 minus 0.06 divided by 2, this is this distance from x squared, because this is the transportation moment. Okay? So basically, we get now the contribution also of this 4 horizontal moment. So this is the second moment of area of this cross section with respect to the x-axis, taking into account that not the whole thickness of the wall is resisting, but only 2 layers out of 3. Okay? Because we are talking about X-lab, not glue laminated timber. So if we replace these values in the formula, so we replace, for example, the area of the wall is 1.468 times 0.06 times 2/3. In the end, if we substitute inside here the value, we get a value of sigma of 2.65 Newton per square millimeter. We need to compare now 2.65 Newton per square millimeter of strength demand in the layer of the wall with the compression strength in plane of the wall itself. So the compression strength, as you can see here, is 3 from this table. 3 times Fe0 LK to the power of 0.8. So since the bolts that we've been using for our cross-lamp are bolts T10, they have 10 Newton per square millimeter of tensile strength parallel to the grain. The compression strength, characteristic compression strength, is given by 3 times 10 to the power of 0.8, so 18.9 Newton per square millimeter. Okay? Yeah. Questa?
Al momento di inerzia J valida, non manca un contributo rispetto a se stessi dei tratti orizzontali?
Yes, it was ignored because I assume it was negligible compared to the transportation minimum. Yes. So strictly speaking, here we should also add basically the second moment of error goes to red layer with respect to the neutral axis. You can add, if you want to be rigorous, you add it, but you will find that it's very small compared to the other one, because this one, in this case, the transportation bending moment will be related to the square of a length which is, let's say, 10 plus 10, 20 millimeter, while instead this other transportation moment is related, instead of 20 millimeter, to 3 meter, which is 1,000 times more. So for this reason, just ignore it. But strictly speaking, you should keep it. Yes, you should put it. But you will find that it's negative. So in the end, I said we calculate the compressive strength of cross-lamp, 18.9 Newton per square millimeter. And then the design value, 1.1 times, and you see that here, in fact, here I remember to put the right value, so this 1.45 we were discussing before, it was actually put here. So I updated this with the new regulation. So here, since we are talking about cross-lamp now, the gamma n is 1.45, not 1.5. So 1.1 times 18.9 divided by 1.45 is 14.3 Newton per square millimeter. Now we compare the design value with the strength demand. You can see that we are far away. So basically, the strength demand in the cross-lamp panel is by far distant from the strength capacity. In fact, as I was telling before, usually we don't have problem in the cross-lamp panel itself. We can have a problem only in the cross-lamp panel when they're used as a floor. If they're used as a floor for long span, like 6, 7, 8 meter floor, then we may have some problem. Not problem of strength, ultimately, problem of excessive deflection. But when it comes to strength control, usually cross-lamp panel is not a problem. So what is a real problem is the design of the connections. Okay? So this is more or less as a summary of what you were supposed to do for your second design. More or less you should follow this track here. Perhaps do a bit more perhaps about the distribution of the forces, because here it was done using the software, but we said you should do by hand. When I say by hand, I mean by Excel, using Excel. Okay? Any question about this? Okay. So now we're time to start the next example, which is more or less similar, it's very similar, but the next one is based, it concerns light frame walls instead of cross-lamp walls. Okay, so here we have the plans of a very small limestone walls, two-story limestone wall. The design data, I would say more or less the same as the one that we saw for the Prof building. The only difference being the behavior factor. Behavior factor for limestone construction, while for cross-run wall in Italy now is 2.5. For limestone wall is, for limestone construction is 5. So we can use a Q factor of 5. Again, we need to process the loads. So structural self-weight this time is a little bit lower because, of course, the light frame wall is lighter than cross-run wall, so 0.28 kN per square meter. Structural permanent load is 1 kN per square meter. So the total permanent load for the roof, for the roof, is 1.28 kN per square meter. If there's snow, like before, 1.2. Then for the floor, intermediate floor, structural weight 0.21, no structural permanent load 1.75, so the total permanent 1.96. And the imposed load, as usual, being a domestic destination, is 2 kN per square meter. Now we need to calculate the external and interior walls. So the weight of the light frame wall is 0.1 kN per square meter. If I multiply this by 2.4, which is the height, I can get 0.24 kN per meter of weight of an interior wall. So the weight of the thermal insulation finishing, 0.4, which multiplied by 2.4 is 0.96. So the total permanent load per meter of length of wall is 1.2. So 1.2 kN per meter. Again, we need to do this check that you understood yesterday about regularity in plank and elevation. You are going to choose a building which is regular in plank and elevation. Otherwise, we cannot use the linear static analysis. And then it comes as usual to calculate the seismic weight, exactly like we did yesterday. There is nothing else to say. Exactly like yesterday, we calculate the permanent enforced load and the sign. So permanent, for example, 4.88 is, so the plan is 4.88 by 6.10, so this is the area, the plan of the floor, times 1.96, which is the unit weight, so the self-weight of the floor unit area, plus 1.2 is the imposed load. No, sorry, the imposed is here. 1.2 is the weight per unit length of wall. So 1.2 times 4. So now we are assessing the weight of the walls. So it's one wall, second wall. So 4.88 by times 2 plus 6.10 times 2, so 6.10 is 1 here, plus the second 1 here, 6.10. So 84.70. The imposed load is 2 kN per square meter times this coefficient for quasi permanent load combination, which is 0.3, in order to get only the seismic weight, plus times the area, so 17.86. The total is 102.56. Then we do the same calculation for the roof. The only difference being for the roof that we have the contribution of the wall should be, of the lateral wall should be divided by 2, that we see this over. There's no also here, it doesn't count anything. So in the end we get the total seismic weight of 157.65 kN. Same concept as the one that we saw yesterday for cross-run walls. Estimation natural vibration period, exactly like yesterday, like today if you want, so we just use this approximated formula, 0.2 seconds. And then we proceed with the calculation of the base shear, starting from the calculation of the design spectrum, which comes after the calculation of the elastic spectrum. So the same value here, taken from the the place where we're going to design the building. For example, L'Aquila was not L'Aquila, it was Udine or province of Udine. Anyway, those are some values. And then we calculate, like before, the value of S, TC, TB, and TD. So this would be the elastic spectrum, exactly like the one from yesterday. We insert inside the value of the natural vibration period. Again, we are on the plateau. And we calculate now the design spectrum by taking into consideration the behavior factor. In this case, the behavior factor is 5. So we get a value of ST of 0.21. So from the black curve, we move to the blue curve, which is, so from the elastic spectrum, we move to the side, to the design spectrum, where we have an ordinary design spectrum of 1.21. Now we can calculate the base seismic shear, so FD. FD in this case is much lower, it's 33.11. Before we had something like 1 or 300. Because before we had one flow more, and of course the cross building is heavier than the light frame building. Okay? So we need to consider this. Light frame building is much, I would say, significantly lighter than a cross building. So when we design a light frame building, we design for seismic, but strictly speaking, we should also be designing for wind. Because wind may govern the design. Why wind may govern the design? Because the light frame building is lighter than the cross-frame building, first. And the Q factor is higher than the cross-frame building. So the value of the seismic action in a light frame building, since I use a Q factor of 5, will be half than the value of the cross-frame building. Even lower than half because the building itself is lighter. So it will be probably 1/4. Okay? So when we design light frame building, I say this not necessarily for this course. For this course, I'm happy to do only the seismic design. But when you do a calculation as an engineer, please don't forget to do the verification of the wind, particularly also for cross, but particularly for light frame building. Because usually the design is governed by wind modeled by seismic. Okay? Particularly if you use a Q factor of 5. Okay, it's clear to this? Okay, good. So 33.11 kN base shear, and then we do the redistribution of this shear along the height of the building, so we calculate F2 and F1, and then the seismic shear at the different stories, exactly as we did before for the cross slab. Okay? Okay, now strictly speaking, yesterday we didn't mention this for cross slab, but this is true for any sort of building. If you read the regulation, for example, the Eurocode of the Italian regulation for construction, they said that anyway, even if I designed the building in order to have the coincidence between the stiffness center and the mass center, anyway, the regulation asks us to consider an eccentricity, what we call accidental eccentricity. So the accidental eccentricity is at least 5% of the maximum dimension of the building in that specific direction. For example, you can see here, if the building is 5 meters wide, I should consider at least an eccentricity of 5% of 5, which is, so 5 meters, 1% would be 5 centimeters. 5 centimeters times 5 is 25 centimeters. So I should consider an accidental eccentricity of 0.25 meters. Okay? Meaning that even if I have a coincidence between the two centers, I need to add to my structure this torque moment calculated, taking into account this consideration. Okay, after that, I use again, like we said before, these formulas, this analytical formula, to move from the total seismic shear of the building, so this 26.10 here and 33.11 here, to move from this to the actual seismic shear demand of the single wall. The formula, and again, you see again this kind of distribution. So shear forces per unit length again obtained by distributing the historic seismicity in proportion to the wall length, and consider the effect of the torsional bending moment due to the accidental eccentricity. Again, I find those two small walls as the most stressed. Why? Now, the seismic verification that we need to do in these buildings, this type of frame building, are the following. I need to check the shear into the wall. Then I need to check the uplifting of the old down. Then I need to check the shear on the base of the wall. So basically the ball of the base must prevent this kind of slip. And then we have to design basically the lateral joist of the diaphragm in order to prevent this kind of behavior. So we will start with ultimate state of shear of the nail sheathing to frame connection. Just a reminder that the nail sheathing to frame connection is a dissipative connection. Then ultimate state of strength from uplifting of the all downs. All down are, in this case, all down are non-dissipative connections, so we will have to design the all down for the overstrength of the nails. Then, ultimately state of strength for shear of the bolted connection to the foundation. Ultimately state of tensile strength of the closed perimeter beam, non-dissipative one. And ultimately state of shear strength of the nail flooring to the perimeter beam connection, non-dissipative one. So those are all the verifications that we have to do with. Now, starting from designing the shear. So we have selected the most stressed shear wall, and we know what is the value of the shear strength of the wall that must be resisted. You remember the shear strength must be resisted by shear by the nail sheathing to frame connection. So we need to make sure that those nails can resist the seismic demand. And then we need also to make sure that they can dissipate energy. Because we assume that this structure here is dissipative, and we also said that we have to use a Q factor of 5. So we need to make sure that those nails can dissipate energy. So it may form at least 2 plastic hinges. So there is a chapter of Euro 5 dealing with the strength of shear walls that I just attached here for your convenience. And then I summarize here the ultimate state of shear of the nail sheathing to frame connection. So now we have a connection between the sheathing, the frame, and this nail connection may have 6 different value mechanisms. Okay? So what we are talking about now is this connection. This is the frame, this is the sheathing, this is the nail. So we want to check the nail connection in a wall like this. So now we are designing this kind of connection. Okay? This nail connection between the sheathing and the frame. Now, in order to find out the characteristic strength of one nail, we need to know some properties. For example, we need to know the embedding strength of the nail in the sheathing, which is OSB. In our case, we consider a sheathing made of OSB, oriented strand board. So in Italy, the use of OSB is often preferred to the use of plywood. So oriented strand board. So for oriented strand board, we need to find out value from the bending strength. This is a formula, semi-empirical formula that can be used for characteristic and bending strength of the sheathing. T is the diameter of the nail, and T is the thickness. T is the thickness of the sheathing. So this is T. T, diameter of the nail. Then this other formula gives us the characteristic and bending strength of the frame made of some timber. depending on the characteristic density and on the diameter. Then we need to know a formula to calculate the characteristic yielding moment of the fastener. This one, where Fu is the ultimate strength of the fastener. And then the characteristic withdrawal strength of the fastener in order to take into account the Rolf effect. If you go back where we discuss about connection, you will find also those formula to assess the characteristic withdrawal strength of the fastener in order to take into account the Rolf effect. Now, if we calculate, okay, we make some assumption in terms of the nail connection. For example, we use 3.1 times 60 ring sharp nails. So nails with a diameter of 3.1 millimeter and length of 60 millimeter. Those kind of nails are convenient because they can be burned using some gun machine. They can be burned directly without using the hand. Okay? Good. Now, if you replace, we calculate all these values, and we replace this value in this equation here, we will find that we get a characteristic strength of the nail given by 756.5 Newton with a value mechanism D, characterized by the formation of one plastic hinge. Now, if you remember, there is a specific requirement from the Italian regulation to make sure that this nail can be considered as a dissipative, a very dissipative connection in order to be able to use the Q factor of 5. This requirement is about the slenderness of the nail itself. So we need to have a sheathing T with a thickness T, which is at least 4 times the diameter of the nail. In our case, the diameter of the nail is 3.1. 3.1 times 4 is 12.4. The actual thickness of the OSB which is produced is not 12.4 but it's 12 millimeters. So strictly speaking, this wouldn't be okay. But you can understand that the difference of half a millimeter, less than half a millimeter is really something very theoretical. Okay. It's very small. So in the end, we could say, okay, this is more or less 4D. It's not really 4D, but slightly less than 4D, just 0.4 millimeter less. Okay? So we could say that, okay, this requirement is satisfied. Then the second requirement is that the diameter D does not exceed 3.1 millimeter. We chose actually 3.1 millimeter because it does not exceed 3.1. So we could say that this requirement is satisfied. So it is appropriate to use a Q factor of 5 when designing this kind of structure. We can then calculate the design value of the strength of the nail by taking the M-mod, so 1.10, and by taking a gamma 1.5, because we're talking about connection. So for one nail we get this value here. Characteristic value times M-mod divided by gamma n, 554 Newton. So one nail resists 554 Newton, so 0.5 kilonewton of shear strength. Now, the design strength of the shear wall can be given by this relationship here. If you remember, some time ago we calculated for a shear wall the basically value of the strength in one nail, of the shear demand in one nail due to the shear capacity of the wall. So we can turn the other way around the formula and find what is the actual total shear capacity of the wall based on the shear strength of a single nail. And you can see that there is also a factor 1.2 that the regulation, if you look at the Eurocode 5, the regulation said, okay, if you have only one nail or two nails, of course you cannot use this 1.2, but if you have a number of several nails all around the perimeter, this kind of a system effect given by the fact that there are more nails all aligned can lead to a slightly higher strength, a strength which is 20% higher. So this formula says basically that if I have a wall like this, This is FIVRD. So this is the maximum shear strength that this wall can take based on a single strength, shear strength of 1A. So FRD. This is the design strength of a single nail. S is the spacing. B is the breadth of the wall, so this is B, CI. And CI is a coefficient that usually is equal to 1. So, now, we calculated the design strength of 1A. From this design strength of 1A, we can calculate the actual design strength of the whole wall by using this equation here from the equilibrium. We now assume a certain value of the spacing, for example 150 millimeter, which is quite common value. So 1A, 3.1 millimeter every 150 millimeter spacing. And so if we substitute inside the formula, so this will be 0.554, this is the strength for a single nail, times the breadth of the wall, 1.24, times this coefficient 1 divided by 0.15, which is the spacing, times 1.2 will give me 5.5 kilonewton. So the whole wall can resist 5.5 kilonewton of shear. Now we divide this whole shear strength by the length of the wall, 1.24, and we get 4.43 kilonewton per meter. We compare this value of the shear resistance per unit length of wall with the demand. So the size of the demand is 6.5 kilonewton per meter, which means that this verification is not satisfied because the strain demand is lower than the strain capacity. No, sorry, the strain demand is higher than the strain capacity. Strain capacity is 4.43 and the strain demand is 6.5. So the verification is not satisfied. Now, very quickly, because we are at the end of our lecture, how can we make this verification satisfied? We have two possible ways. One way is to reduce the nail spacing. Very, very simple. Instead of placing one nail every 150 millimeter, we place one nail every, for example, 100 millimeter. Second possibility, I can use double sheeting. So instead of using a sheeting only on one side, I can use a sheeting only on the other side. I have a frame, and with my sheeting on one side and my sheeting on the other. So basically what I do, I duplicate the sheeting. So this is the frame, and then I have one sheeting on one side and one sheeting on the opposite side, which will basically double up the resistance. So if I reduce the nail spacing to 100 millimeter, as you can see here, I get 8.24 kilonewton. So I get 6.65 kilonewton per meter, which is greater than 6.5. So by reducing the spacing from 150 to 100 millimeter, I get the ultimate limit state of shear fully satisfied. Now, just note one thing, and now we stop, because we will continue tomorrow. Just note one thing. And now, if we decide, for example, to reduce the spacing by 150 or 200 millimeter, the ultimate limit state verification is satisfied. And note that now the connection is slightly oversized with respect to the actual strain demand by another design factor given by, you see, this is the strain demand 6.5, this is the actual strain capacity. So 6.65 divided by 6.5 is 1.02. What is this 1.02? It's what we call over design factors. So my shear connection is slightly oversized with respect to the minimum value that I need. So strictly speaking, I should have put not one nail every 100 millimeter, but probably one nail every 102 millimeter. If I put one nail every 102 millimeter, we'll get here 6.5, exactly the same as this. While instead, since I don't put 102, because it doesn't make any sense, if I put 100, 110, 120, put 100, and a slightly oversizing of the nail connection. This over design factor is 1.02. Why is this important? Because, here I finish, because now we have designed the only dissipative component of our structure for the actual design spectrum obtained by using the Q factor of 1. Now, all the other components, for example, the output, for example, the under brackets, everything else will have to be designed not for the design spectrum, but for the overstrength of the nail connection using capacity-based design. Tomorrow we're going to see that, for example, in order to get the force of the old down, we will have to start from the actual strength of the nail and to work out what is the value of the force in the old down, which is associated to the actual strength. And we need to keep in mind that the actual strength is slightly higher than the strength demand because we have this over design factor. And then we will have to use the over strength factor. Okay? Any question? Okay. Just remind you, tomorrow we see you here at 9 o'clock and we do more or less 3-4 hours what is needed to finish this presentation and to finish the fire safety presentation. Okay? And then you will have some of you, I think you will have to discuss with Dr. Cementa about the design probably. If you have tomorrow, there is also a possibility with Dr. Cementa to do a revision for the project, because I think that some of you are working continuously on the project, so you might have some questions to clarify with her at the end of the lecture, okay? Okay, thank you, and see you tomorrow.